Welcome to the office. We want to take a look at another example working with a quotient group here. And our goal for this example is again to find the order of the quotient group and then find the order of an element within that quotient group. What makes this example more interesting than the previous is that we're no longer working within an abelian group. Right? We know that D4 is not abelian, and we're taking a direct product of Z12 with D4. So we've added the layer of complication of a non-abelian group, not that it's actually any complication, as well as added the additional aspect of direct product, which again doesn't really create any significant complications. We just need to say, okay, well, we're in a slightly different situation, and how do we handle direct products? How do we handle elements in the dihedral groups, right? So we just have to say, okay, well, it's different, but handled pretty much the same way as we've been handling these examples so far. So we want to find the order of the group. Now, we talked previously that in our development for the proof of Lagrange's theorem, that we said that of course, the number of cosets of a subgroup times the number of elements in the subgroup gives us the order of the group. Yep. That's essentially what we're looking for. That works for finite groups anyway. So since we know that Z12 direct product with D4, we know that this has an order of 12 times 8, because this is order 12, this is order 8, and then we're taking ordered pairs of those. So this is 96. Right, that's less than infinity, which means that it's finite. So working with what we had talked about developing our proof for Lagrange's theorem, we know that the order of the direct product is equal to the order of the subgroup times the order of, the number of cosets, rather, which is the thing that we're actually interested in here. Excellent. We already showed that this is 96. What I'd like to do is I'd like to consider the order of this element or the order of the subgroup that's generated by that element. Either one is fine. The order of the element 4 in Z12 is 3. And the order of row 1 is 4. Of course, that's in D4. So the order of what's generated by 4 and row 1 is going to be the least common multiple of 3 and 4, which is 12. This gives us that 96. 96 is equal to 12 times the number that we're actually interested in finding. Z12 direct product with D4, quotient by the subgroup generated by the element for row 1. Division by 12 gives us that the order of the group Z12 direct product with D4 mod what's generated by 4 and row 1. 96 divided by 12 gives us 8. Now you might be asking, what do those 8 elements look like? Can we do the same thing as the previous example where we write all of the elements in Z12 direct product D4 and then say, these are in one coset and these are in another coset? Well, you could if you wanted to, but that would be writing out all 96 elements. So I'm not particularly interested in doing that. That'd be very time consuming. You could. but it's not necessary. We don't want to rely on that. So we have answered the question of what is the order of the quotient group. Now I want to consider a particular element in the quotient group and determine the order of that element. You'll notice here that the operation that's written is that of multiplication because it is considered the generic representation, right? Multiplication is the generic representation for a binary operation. So the binary operation in Z12 is addition. The binary operation in D4 is composition. They don't match, so I'm just using the generic representation of multiplication for the binary operations. All right. At this point, what I want to do is I want to recognize that I'm going to cycle through these things, right? This raised to the first power, of course, is not the identity. This thing squared represents 7 plus 7, and delta 1 composed with delta 1, so delta 1 squared. This thing to the third power is 7 plus 7 plus 7, or 3 times 7, and then delta cubed, right? We have these representations for the direct product, the representations for multiplication here that I'm using to represent our binary operation, and then the individual representations inside of that direct product. All right. So when does this become the identity element? Well, in order to recognize that, what we need to do is we need to recognize the order of the individual pieces inside of this, and then take their least common multiple. So I want to find, essentially, I'm taking Z12 mod what's generated by 4, and then working with that. And then taking this thing, D4 mod by row 1, and when does that give me an identity element? And then working with the least common multiple for us to cycle through and get to what we're looking for. All right. Now, order 96, order 12, this has order 3, this has order 4 inside of there. Yep, okay. So find the order of this thing. So the identity element in our quotient group, Z12, direct product with D4 mod, what's generated by 4 row 1. This is equal to, let's see here. Oh, not equal to, but is the identity element in, I don't need those bars either. The identity element in this thing is, so what would be our identity? 0, comma, row naught. All right, the identity is always going to be one way to represent it. Identity in Z12, identity in D4. But when do I get those? From these, right? That's another way to think of it. So this is going to be 4k, comma, row 1 to the k times 4 row 1. There we go. So I want to make this thing look like that. Now, I can't get delta 1 to look in general like a rotation, except for delta 1 squared is row naught, the identity element. So I want to notice that delta 1 squared is equal to row naught. So the order of delta 1 is 2. That's what I'm interested in observing there. And the least common multiple of 7 and 4. So similar to what I was looking at earlier, 7n or 7 times n is equal to 4 times k, trying to set up that sort of thing here. This is equal to 28. So I want for, I want to choose for n is equal to, I'm sorry, 7n, 7 times n is equal to 28. And that is n is equal to 4. So I have the order of this thing, and I have the order of this thing. So this essentially tells me that the order of delta squared, sorry, the order of delta 1 is 2, and the order of 7 is 4. And so I'm looking for the least common multiple of 2 and 4, which is just 4. Now I can take 7 delta 1 product with what's generated by 4 row 1 and raise it to the 4th power to recognize that this is exactly 7 delta 1 to the 4th power times what's generated by 4 row 1. And this is equal to 4 times 7 delta 1 to the 4th power times what's generated by 4 and row 1. This is 28, and delta 1, we could write this as delta 1 squared if we wanted to, if that is helpful. This is the identity squared is the identity, and this is also 0, so we get 0 row 1. I'm sorry, row 0. Oh, and I'm missing parentheses on a few of these. That looks better. So the order of 7 comma delta 1 times what's generated by 4 row 1 is 4. Awesome. That looks good in terms of one minor check that we could do is make sure that the order of the element divides the order of the group. And it does in this case. So, right, that doesn't guarantee that we have a correct answer, but it does, it would tell us if we had an incorrect answer. So that's a good double check there. So it is still a lot of least common multiples and understanding how we're constructing these things to build up our direct products, for example, but as well as what does it look like to have what are our elements in our dihedral groups, and what does it look like to mod by some group or subgroup rather. So there's definitely a lot going on here. We're going to take a look at another theorem. Actually, another couple theorems and a definition, and then follow it up with a few more examples to wrap up this section. So join me for a little bit more on factor groups.